In this video, we shall discuss on time series. You will learn all you need to know about time series. First, we'll start with the definition. Definition. For more on this topic, you need to subscribe to this channel. So the time series as a stochastic process is an ordered sequence of value. The time series is a collection of observations made sequentially in time. So time is very useful in time series, and as a stochastic process, it's an ordered sequence of observation. Yes, we also define the time series to be a collection of observation made sequentially in time. And sometimes we denote the time series to be xt, which is the value of the observation. That is for that. Now, the ordering is usually in time. The ordering is usually in time. Now, the time series occur in variety of fields. Variety of fields. Fields for time series. The time series occurs in varieties of fields. For example, we can find the time series in agriculture. We can find time series in business and economy. Business and economy. We can also find time series in engineering. We can find time series in geophysics. We can find time series in medical science. We can find time series in medical sciences. Okay, 5. Medical sciences. 6. We can find time series in metrology. Metrology. 7. We can find time series in quality control. Quality control. We can also find time series in social sciences. Social sciences. So these are the areas or the fields where we can find time series. We can find it in agriculture, metrology, business and economy, engineering, quality control, geophysics, social sciences, medical sciences. Now, objectives of time series analysis. Objectives. Objectives of time series analysis. So what are the objectives? 1, we'll have the description. 2, we have the explanatory or explanation. 3, we have the forecasting. Forecasting or prediction. And 4, we also have control. So these are the areas where these are the objectives of time series analysis. When we talk about time series analysis, these are simply the objectives. These are simply the objectives. So a simpler, more useful way of describing a stochastic process is to give the moment of the process. Is to give the moment of the process. Now, the first and second moments are the mean. I mean, the first and second moments of time series analysis. A much more easier way of describing the time series is, like we have just said, is to give the moment of the process. To give the moment of the process. Now, we say the first and second moments of time series. Now, we have to put down the first and second moments of time series. One, we have the mean. The mean, which is also denoted as this, we write it as this, is equal to the expected value of xt, which is the value of time series. Also, we have the variance. We have the variance. The variance, which is denoted as this, can be written as the variance of xt. And this is also equal to, so we'll move over to this other side of the board to finish up that. We have to clean this side. For more on this topic, you need to subscribe to this channel. So we can now write the variance properly. The variance, we can complete it as the variance of xt is equal to the expected value of xt minus mu t all squared. So that's the variance. So the variance for the first and second moments of the time series can be written as this. Or we have again the covariance. The covariance, which we can denote as R into T1, T2. We can write it to be R T1, T2 to be equal to, now we can write the covariance of xt1, xt2, which is also equal to the expected value of xt minus mu t1 multiplied by xt2 minus mu t2. So this becomes our covariance. And the fourth one, this becomes our covariance. That means the first and second moment of a time series. Because before you can describe a time series, you must first describe the process or the moments of the process as we talked about before. Now, the fourth item we have is the correlation. The correlation function for the fourth one. So the correlation function can be denoted as the covariance of T1, T2 between X T1 and X T2, and is defined as our correlation of T1 T2 is equal to the covariance. I'll write it out properly this other side. The covariance of xt1 xt2 divided by the square root of the variance of xt multiplied by the variance of xt2, the variance of xt1 and the variance of xt2, which also can be written as r t1 t2 all over the square root of sigma squared 1 t1 multiplied by sigma squared 2 t2. So I'll have to write this out properly. I'll write it out properly. To move over to this other side of the board to do that. So move over to this side to write the fourth item. Oh. For more on this topic, you need to subscribe to this channel. So this is just the peripheral of what we are to discuss. Like we have said, a simpler, more useful way of describing a stochastic process, which is a time series, is to give the moments of the process. So we have our correlation to be T1, T2. We are writing it out properly to be the covariance of xt1, xt2 all over the square root of the variance of xt1 multiplied by the variance of xt2, which is also equal to r t1 t2 all over sigma squared 1 t1 multiplied by sigma squared 2 t2. So this is simply the first and second moment of the time series. So this is how we can describe the time series. The next thing we are to go into is stationarity, but we'll discuss the autocovariance and the autocorrelation function. We'll discuss the autocovariance and the autocorrelation function. For more on this topic, you need to subscribe to this channel. In this video, we shall discuss on the autocovariance and autocorrelation function of a time series. Now, the autocovariance and autocorrelation function can be denoted as the autocovariance can be denoted as RK, while the autocorrelation can be denoted as PK. Now, for we to analyze this properly, we need to check their properties. We first state their properties. After stating their properties, we still have to prove these properties if they are correct. One, the first property we have is, we say the autocovariance is equal to the variance of our time series, and the autocovariance is equal to the variance of our time series, and this implies that our autocovariance is equal to 1. This is the first property. The second property, we have our autocovariance RK is equal to R minus K, which also implies that PK is equal to P negative K. You can call it like that. Also, the third property we have for the autocovariance and the autocorrelation function, we have the third property to be RK is less than or equal to R0, which implies PK to be less than or equal to 1 for all K. So this is the property for the autocovariance and autocorrelation function. The first thing we need to do is to prove this function one by one. So we come here, we write proof 1. The first one on our list states that R0 is equal to 1. And by definition, RK is equal to the covariance of xt and xt plus k. So we can say for k to be equal to 0, we'll have R0 to be equal to the covariance of xt plus k, which is equal to the variance of xt. Also, we can note that we say given the variance of xt to be equal to 1, we have R naught to be equal to 1. That is R naught, which is our covariance, to be equal to 1. So this is simple. Also, we can also remove this xt plus k. So if we have this, since our variance is also equal to xt, since our variance can be written as this and is equal to this, and our variance is also equal to 1, at k equal to 0. So we can have that. So if k is equal to 0, it implies that R naught is equal to the covariance of xt, which is equal to the variance of xt and the variance of xt is equal to 1 since k is equal to 0. So if we input k is equal to 0, this turns to 0 automatically, so we can have this as this. We can have this as this, as simple as ABCD. So this ends our proof, but this is where k comes in. We have xt. So that's the proof for the first one. For the second one, rk is equal to r negative k. We can do it here. For more on this topic, you need to subscribe to this channel. Proof for the second one, we are given rk to be equal to r negative k. So this is what you have to prove. So from stationarity, the covariance depends only on log k. From stationarity, covariance depends only on log k. So since it depends only on log k, we can have our rk to be equal to, let's delete this part, thereby having this in mind too, we'll delete this. So our RK can give us covariance of xt plus k. Also, r negative k is equal to the covariance of, this can move over to this side. So we can write it as then xt minus k. So it then means that if this is equal to this, it then means that we can say but the covariance of xt and xt minus k is equal to the covariance of xt minus k and xt. Of course, we say let s is equal to t minus k. If s is equal to t minus k, then the covariance of x and x plus k, we can write it as this. Thus, we can move over to this other side of the board. Thus, if this is true, if what I've written here is true, then we can write thus rk, which is our covariance function, is equal to r minus k. So the next one we go into is r number 3. So prove our number three. That number three, if you could remember, we are asked to prove how k is less than or equal to 1. From Cauchy-Schwarz inequality, from Cauchy-Schwarz inequality, we can remove this. For more on this topic, you need to subscribe to this channel. For Cauchy-Schwarz inequality, the covariance of xt plus k is equal to, okay, since it's bounded, is less than or equal to the variance of xt multiplied by the variance of xt plus k. So we say, but the variance of xt plus k is equal to the variance of st and is equal to 1 for stationarity. Is equal to 1 stationarity. Then we can simply write first to complete our proof or to show. We can simply write R, which is our covariance, is less than or equal to the square root of, since this is 1, we have 1 times 1. So we have 1 multiplied by 1, which is equal to 1. So we have succeeded to say therefore RK is less than or equal to 1. So we have succeeded in proving the properties of autocorrelation and autocovariance function of a time series. For more on this topic, you need to subscribe to this channel to get more on time series analysis.